So energy cannot be created or destroyed. Any comments on that statement? Any questions that come to mind?
So energy can only be gathered or transferred.
Right. Yeah, you can concentrate energy in one place. You can move it from one place to another. You can convert it from one type of energy to another, just like Dennis converted one of his blocks into gases. Right. It's still, but it still existed, in a sense. So there's a fixed amount of energy in the universe, and as far as physics has been able to determine, you can't make it come out of nowhere, and you can't make it go away. All right. So let's talk about what that means for a given system. First of all, we have to remember, like we gave the definition for energy, that it's the ability to do work. But here's another way of describing it. It's a fixed quantity that can be calculated for any given system, that before and after whatever's going to happen inside that system happens, the number remains the same. So let's give an example. Let's start with a swinging pendulum, because it's a real good example. So here's a pendulum, and it's swinging back and forth. And when it swings here, it swings to a height h. Okay? So when it's in this position, here's the mass of the pendulum. Who knows what the formula for the energy of that pendulum, right, is at the epigee, or the top of its swing? Who remembers? Andre.
Is it the mass of the object times the height that it's at times the acceleration of gravity?
Acceleration due to gravity.
Acceleration due to gravity.
Exactly. Good. So please commit this to your notes, that the energy, what is that type of energy called when the ball is just at the very top of its swing when it's not moving? Michael?
Isn't it a bunch of potential energy?
It is potential energy, yes. In this case, yes, a bunch of potential energy. Yeah. So EP, this is potential energy, is mgh. Yes. mgh. Now, when it's at the bottom of its swing and it's cruising along there, it has a different type of energy. What's it called at the bottom? Anybody know? Michael.
Wild shot kinetic energy?
Yeah, excellent. Kinetic energy. Right, that's the energy of motion. So EK, so kinetic, KI or KE? I can't spell it close. Kinetic. That doesn't look right. Yeah, it's got to be. Sorry, guys. Kinetic energy, EK, is, anybody remember the formula for kinetic energy? It's a little trickier. Andre.
It's the mass of the object times its velocity squared.
Very close. A little bit different. 1/2 mv squared. It's 1/2 mass times velocity squared. That's the kinetic energy. So you can do a lot with the energy formulas, because you know that EP must equal EK. EP must equal EK. Sorry, hold on a second. When the potential energy when the ball's at the top must equal the kinetic energy when the ball's at the bottom. And the total energy, E total, which equals EP plus EK, must remain the same at all times for the system. So let's do an example with this. Let's do a real simple example. So, again, we'll use our pendulum. The pendulum is released from a height of, say, 1 meter. The pendulum weighs 1 kilogram. We want to know, what is the velocity going to be when it reaches the bottom of its swing? That's the question. Anybody want to give a description of how you think we can solve that? Andre.
I believe you set the equation for the potential energy equal to the equation for the kinetic energy at the second position.
Right. Yeah, that's right. And so let's do that. Let's do that. So we're going to say, I'll write the equations up here to start with. So E potential is mgh. E kinetic is 1/2 mv squared. So we set the two equations equal to each other. So mgh equals 1/2 mv squared. What do you notice immediately happens to these in this equation? Kind of strange thing that happens. Yeah.
Masses cancel out.
Yeah, the masses cancel out immediately. Weird. You don't even need to know the mass. So watch. Mass cancels out. So now GH is 1/2 V squared. So I'll multiply both sides by 2 to get rid of the 1/2. So that goes away. So 2GH equals V squared. Now I'll take the square root of both sides of the equation to get rid of that squared. So then we can rewrite it as V equals 2GH. So the velocity is going to be 2 times 9.8 times a height of 1 meter, which equals, what does that come out to? Yeah, 19.6. What's that?
Yeah, I missed that.
No, I took the square root of, oh, I'm sorry. I dropped this, I accidentally dropped the square root. That's right. This whole thing is square rooted. Sorry, let me rewrite this. Sorry, guys. Good call. Yeah, it's not squared, it's square rooted. So V is the square root of 2GH. Okay, so we can calculate that. G is 9.8. The height is 1 times 2. And so 19.6. The square root of that is 4.43. So the velocity is 4.43 meters per second. What does that tell you about a pendulum system? There's something really interesting that tells you about pendulums. The whole of the equations, the process we just went through, specifically the observation that Andre had at the beginning. There was something interesting that happened with the equations.
The mass does not matter. The mass doesn't matter in the conservation of energy?
Okay, the mass doesn't matter, but when we talk about pendulums, what does it mean if I have two pendulums and I have one with a Nicholas?
So it doesn't matter what the mass is. A pendulum it will always swing at the same rate.
Yeah, it'll always swing at the same frequency, or I'm sorry, it'll always swing at the same. The velocity will always be the same if you raised the mass to the same height. It's independent of mass. And how this works out with pendulums is what determines the frequency of the pendulum is only how long the string is, not the mass that's attached to it. All right? It's interesting. So this is one way of using energy. in the next lecture, we'll talk about yet another.